Our learning objectives are the following. Graph exponential functions, identify data that displays exponential behavior, solve problems involving exponential growth, and solve problems involving exponential decay. Let's begin this lesson by asking, what is an exponential function? An exponential function is a function of the form y equals a times b to the power of x, where a is not equal to 0, b is greater than 0, and b is not equal to 1. Exponential functions are nonlinear. Let's now look at how to graph exponential functions. For an exponential function, the graph of y equals a times b to the power of x changes according to the values of a and b. For a growth function, a is greater than 0 and b is greater than 1. You can see that in the example that we have here, that this function of x equals 2 to the power of x. So in this case, b power of 2 is greater than 1, and it will start from the left-hand side and increase towards the top right-hand side of the graph. For exponential decay, the power of a will be greater than 0, and the power of b, or the variable b, will be between 0 and 1, still to the power of x. So in this case we have a function 1 over 2, or a half, to the power of x, and in this case it will start on the left-hand side, be a large value, and decrease towards the right-hand side of the graph. Now that we've seen what the exponential growth and decay functions look like, let's analyze their behavior to see what the properties of these functions are. Firstly, for exponential growth functions, remember this is where the value of b is greater than 1. The domain, or x values, it will take are for all real numbers. The range of y values will be all positive real numbers. For the intercepts, there will be one y-intercept and no x-intercepts, the reason being that the x-axis is an asymptote. And the end behavior, as x increases, function of x increases, and as x decreases, the function of x approaches 0. For exponential decay functions, this is for the value of b being between 0 and 1, or a fraction or decimal value. The domain will be, again, all of the real numbers. The range of y values will be all positive real numbers. The intercepts, again, it will have one y-intercept and no x-intercepts, as the x-axis is an asymptote. However, the end behavior will change. As x increases, the function x approaches 0, and as x decreases, function x increases. For our first example, let's look at a function that models exponential growth. Graph the function y equals 3 to the power of x, find the y-intercept, and state the domain and range. First, let's construct a table of values. In the first column, we have the x values, -2, -1, 0, 1, and 2. In the second column, we have the function itself, so substituting in those x values, we have 3 to the power of -2, 3 to the power of -1, 3 to the power of 0, 3 to the power of 1, and 3 to the power of 2. In the final column, we will have the y values, which are 3 to the -2 is 1/9, 3 to the power of -1 is 1/3, 3 to the power of 0, 1, 3 to the power of 1 is 3, and 3 squared is 9. So the graph crosses the y-axis at 1. Clearly see here that where x equals 0, y equals 1. The domain is all real numbers. The range is all positive real numbers. The graph approaches the x-axis, but there is no x-intercept, and the graph is increasing on the entire domain. We can see that the x values are increasing, so the y values are also increasing from 1/9 up to +9. What does that look like as the graph? Well, if we look at those values again, we have -2 and 1/9, so that will be this value here. We have -1 and 1/3. So just above the x-axis, we have the graph crossing over at 0, 1. That is the y-intercept. And then we have the values of 1 and 3, and x equals 2 and 9. And you can see that the graph of y equals 3 to the power of x is clearly increasing from left to right. In this second example, let's look at graphing a function of an exponential decay. Again, let's start with a table of values. So we have x equals -2 to +2. We'll look at the substituting the values of x into the equation of 1/3 to the power of x, so 1/3 to the power of -2, the power of -1, and 0, 1, and 2. So what will happen in this example is that 1/3 to the power of -2 is actually 9. 1/3 to the power of -1 is 3. 1/3 to the power of 0 is 1. And 1/3 to the power of 1 is 1/3. And squared is 1/9. So what's happening with this particular function? The graph crosses the y-axis at 1, so the y-intercept is equal to 1. The domain is all real numbers. The range is all positive real numbers. The graph approaches the x-axis, but there is no x-intercept. However, this time the graph is decreasing on the entire domain. So you can see that as the x values increase, down here, going from -2 to +2, the y values are actually decreasing from 9, 3, 1, all the way down to 1/9. And therefore the function this time will start with -2 and 9. Its value on the left, and go down to 3, then 1, and keep decreasing 1/3, 1/9, all the way down towards, but not crossing, the x-axis. So far we've looked at exponential growth and decay in their most basic forms. However, we can extend those concepts to write a general equation that can be used for exponential growth. The general equation is y equals a multiplied by 1 plus r to the power of t, where a is the initial amount, t is the time elapsed, r is the rate of change expressed as a decimal for r greater than 0, and y is the final amount.
Now before we continue, please don't forget to like the video and subscribe to our channel. As a reminder, we offer private and group online math lessons on Zoom, where we cover all UAE National Curricula, American and British curriculums. We also have the best MSAT math test preparation course with a 50% discount for groups. The first session is always free. So if you are interested in a free lesson, click the link in the description below. To book a lesson you can always send us a direct message on Instagram at Mr. Mathematics. Okay, with that said, let's get back to our lesson.
Let's take a look now at how we can use this in an example. The prize for a radio station contest begins with a 100 dirham gift card. Once a day, a name is announced and that person has 15 minutes to call and claim the prize. If the prize is not claimed, it increases by 2.5% for the next day. Part A. Write the equation to represent the amount the gift card is worth after T days with no winners. So to write that as a general equation, we start off with y equals a times 1 plus r to the power of t. We know that a, the initial amount, is 100 dirham, and we know that the rate that the prize increases by is 2.5%, which we need to express as a decimal, 0.025. So, to substitute those values in, we have 100 times 1 plus 0.025 to the power of t, or more generally, y equals 100 times 1.025 to the power of t, where y is the value of the gift card in this case, and t is the number of days since the contest began. Part B of the question is asking how much will the gift card be worth if no one wins after 10 days. If nobody has won after 10 days, then t equals 10. Y equals 100 times 1 plus 0.025 to the power of 10. So y equals 128.01. So after 10 days, the gift card will be worth approximately 128 dirham. Exponential decay operates in a similar fashion to exponential growth, but in exponential decay, the original amount decreases by the same percentage over a given period of time. A variation of the growth equation can be used as the general equation of exponential decay. You can see that in this case y equals a times 1 minus r to the power of t. So the 1 plus r has changed to 1 minus r, where a is the initial amount, t is the time elapsed, R is the rate of decay expressed as a decimal, and Y is the final amount. Using an example, let's take a look at how the formula for exponential decay operates. A fully inflated raft is losing air at a rate of 6.6% every day. The raft originally contained 74,000 cubic centimeters of air. Part A, write the equation to represent the loss of air. So here we have the initial amount A of 74,000 centimeters cubed. R, in this case the rate of decay, is 6.6% or 0.066. So using the equation, we have 74,000 times 1 minus 0.066 to the power of t. So in this case, you are going to get a number inside the brackets that is less than 1, and that's where the decay rate comes from. So final equation, y equals 74,000 times 0.934 to the power of t. B, estimate the amount of air left in the raft after 7 days. We want the amount after 7 days, so t is 7. So using the equation from the left-hand side, we have 74,000 times 0.934 to the power of 7, which gives an answer of y equals 45880. So the amount of air in the raft after 7 days will be about 45,880 cubic centimeters.